Hi, welcome to Concept Topology, 11th live session and NPTEL NOC 74 course. This is Shavik, and I'm working director of Costing at IIT. So this is the 11th session. There are only two sessions left. One is the 12th session, and another there I will check on one extra session. Okay. So the 12th session will be in upcoming Friday, and the another session will be on up in the the Saturday after the next Friday. Okay, and from 5 to 7. Okay, sorry, 5 to 6. Okay, so okay, so let's get back to our okay. So yes, okay, Avinash is here, right? Okay. So Avinash, let me wait a minute, kindly wait a minute. So Avinash, let me know, do you have any question or any doubt from um, the previous session or any other session? You have any question or doubt? If you have any doubt, please let me know. Okay, let me check the chat here. 1 minute. Okay, Avinash, can you please let me know whether am I audible or the screen is visible to you or not? Okay. Can you please let me know whether am I audible or uh, and is the screen is visible to you? Okay. Okay. Thank you, Avinash. Okay. So now, let's one. Okay. In the meantime, if you have any doubt, you can ask me, of course, or else you can type in the chat also if you have internet issue. Okay. Okay. So now, okay. So now, let's try to solve some questions which I identified some different questions and different assignments. Okay. So, so the first question is the following. First question is the following. Suppose let X be a compact topological string and F from X to 0 infinity be a continuous function. Show that there exists r greater than 0 such that fx is greater than or equal to r for all x belongs to x. So what is the question? The question is given as follows. So we have some compact topological space and f is the function x2 open 0 infinity be continuous. We need to show the such that the x are greater than 0 so f is greater than r. So we need to show that we have some r so the f x. This means what? If we have a function here from x2 from 0 to 1, so the function f always have a minima. So this is the same thing we have to the matrix by the topological space also this is true. Okay, so okay, so in order to prove this, you there is nothing extra we need to use. You only need to use the compactness or connectedness thing. Okay, so let me know how to solve this problem. Think about it. I shall back for 2 minutes. Think about it. I shall back for 2 minutes. one. Okay. So okay. So how to solve this? So okay. So look. So basically, what you need to you somehow need to use the compactness of the given function, right? So suppose X is compact. So of course, fx subset of open 0 infinity and fx is a compact subspace. Correct? This is the first thing. Okay. Now, so this means fx will be closed and bounded. Correct? Okay. Subset of R. Okay. And of course compact. Okay. So this implies what? Fx can be written as union of closed AB A1 B1 dot union of N Bn. Okay. That AI is equal to minimum of U1 to A. So this is what? This is Fx greater than equal to A1 AI for all x. Okay. So basically, without considering compactness, sorry, in this question, the extra thing that is given is the sorry. I mean, so okay. So in this question, the only compactness given, right? So instead of compactness, 1 minute. Okay. So instead of compactness, if we some put additional assumption, namely connectedness. Suppose here we are compact plus connected. So this implies what? Fx will be what? Fx will compact also and connected, right? So in that case, Fx will only of the form open AB because compact connected subs become real and open AB. So in that case, Fx is equal to A. Okay. So that's all. I mean, okay. So the point is that this problem can be solved in a very different way. But anyway, um, this is the one way of solving this problem. Okay. Now the next question. Next question is that let me know is this question is this uh, is the argument clear to everyone or not? Okay, I have this argument is clear. Next question. Give an example of a Lindelof space which is not compact. Think about it. So we need to find an example of Lindelof space which is not compact. So we have already done this particular problem previously, but just for sake of practicing, um, think about it and let me know. So find an example of a space which is Lindelof but not compact. Okay. Consider R with usual topology. Of course, R is not compact, but R is second countable. So R is Lindelof. Okay, see, in order to show something is Lindelof or not, don't try ever to directly prove that every open cover count will suffer, because this is the definition. And of course, in random space, you directly cannot prove the definition using something as a definition. So somehow you need to use it. Lindelof comes from second countability. Okay, so you need to find some space with second countability basically not compact. So this will give the answer. Okay. So this is the second question. I mean, okay, so there are many examples, but possibly this is the easiest one. Okay, now the next question. The next question is as follows. Let x comma d be a metric space and xn be a sequence in x, converge into x belongs to x. Then show that the set xn x belongs to n union singleton x is compact. So basically, what is the question? The question is that what is the question? The question is that if one. So what is the so basically in this question, so in this question, we need to show that if we have a given sequence and suppose the sequence converges to some point x, then the sequence along with the point that set will be compact. Okay. Okay. So try to prove this using definitions. Okay. I shall wait for few minutes. Try to prove using definition only. Okay. 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 So let's try to prove this definition. So in order to submit compare what we need to show, let we need to start open cover, we need to show it as a countable cover, right? So let U alpha be an open cover let U alpha be an open cover of X. Okay. So choose alpha naught such that x belongs to U alpha naught. Correct. So this implies what? This since the now look, since the sequence xn converges to x, so here with the n greater than equal to k such that after finite term xn will belong to U alpha naught for all n greater than k, and x1 and let xi belongs to ui for all I with 1 less than I less than k minus 1. This implies the e1 dot dot dot, kindly hold a minute please. Hello. Okay. Okay, so this implies what? So this implies what? E1 u2 dot dot u n u alpha naught. This thing contains the whole sequence set xn union that limit point also x. Okay. So these implies what? The original sequence at xn union is compact. Okay. So this is the argument. So basically here what we have done, what we're doing, we have some u alpha open cover, and then we start the limit point. Since since we have some limit point of the sequence, so after for finite number of term, all the term will lie in the neighborhood where the limit point will lie. So only there are only finite many points left from the sequence. So the finite limit point will lie in the finite subset of that open cover. So this means what? This means the original set x in x is compact. Okay. So this is the argument. Let me know till now. Do you have any doubt or any question? Let me know till now. Do you have any doubt or any question? Okay. Okay. So now let's go to the next question. Okay. The next question is the following. I leave it. I shall be back in 2 minutes. হ্যাঁ বলো কি হ্যাঁ মাসি ভালো আছি হ্যাঁ বলো 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 না না নেই না না নেই হ্যাঁ ঠিক আছে পরে দেখছি আচ্ছা আচ্ছা ঠিক আছে পরে হ্যাঁ ঠিক আছে পরে পাঠাবো তো ক্লাসে আছি বুঝলা আমি পরে ফোন করছি বুঝলা হ্যাঁ হ্যাঁ ঠিক আছে ক্লাসে আছি পরে বলছি ঠিক আছে হ্যাঁ ঠিক আছে হ্যাঁ হ্যাঁ ঠিক আছে Okay. So, so okay. So let's go get to the next question. What is the question? The question tells that um, okay, uh, a metric space. Wait a minute. Question is a metric space x comma d is said to be totally bounded if for each epsilon greater than 0 there exists finally many point x1 x2 xn belongs to x such that x equal union b epsilon I equal to 1 to n. Okay, the question is that show that every compact metric space is totally bounded. Now the question is the converse true? Justified. So what is the thing? So there is a here is some definition of a metric space that is totally bounded. Okay, 1 minute. So here is some definition of a metric space that is totally bounded. Means what? Uh, for all epsilon, there is a finite many point x1 x2 xn such that x equal union b epsilon xi. Show that every compact matrix are totally bounded. Now, question is the converse true or not? Okay. So, okay. So, okay, think about it. For proving this, what we need to do, we somehow need to. Okay. So first, let's show that every compact is totally bounded. Okay. So of course, here we only need to use the definition. Well, the problem is quite tricky. Okay, I shall wait for 1 or 2 minutes. Let me know. we were able to get the answer. Okay, so let Xg be a compact metric space and epsilon greater than 0 big difference. Okay, then P epsilon x forms an open cover of X. Okay, so till now everything is clear, I hope. Okay, now compactness X implies that there exists a finite subcover for X. That is, there exists finitely many x1, x2, xn belongs to X such that X equal to union of B epsilon xi. So the converse is not true. Question is why? That is not every totally bounded metric space is compact. As an example, for this, consider x equal to open 0, 1 with usual metric. Then x is totally bounded. This is because why? If we have given any epsilon greater than 0, choosing n belongs to n such that 1 by m less than epsilon. And so there exists finitely many points 1 by n, 2 by n, n minus 1 by n belongs to X such that X equal to B epsilon of I by n, I is equal to 1 to n minus 1. But however, X is not compact. Why? Because the open cover 1 by n comma 1 for X does not admit any finite subcover. So this argument. Wait a minute. So how this solution goes? So suppose we have some compact matrix x comma d and epsilon greater than 0. There we are taking the open ball around x. This one open covered. Now compactness of x implies there is a finite sum for x. There is a finitely many x1, x2, xn such that so there uh, yeah hi Ben. So okay, so after repeat. So are you asking me to repeat this question itself, which is right now we are discussing, or are you asking to repeat some previous question? I am asking this because I don't know whether the chat you have sent and it is right now looking this visible in the screen. Uh, okay, okay. So let me repeat the argument here first. Okay. Let's start with definition itself. So what is the question? The question is that X is some given metric space which is totally bound. Now this metric is totally bounded if 40 and epsilon greater than 0. We are able to find a finitely many points x1, x2, x. Then in X as the X equal union of B epsilon xi. Hmm. Now question is first every compact metric is totally bounded. So for this what we have done. Okay. So so compactness of X implies that we have some finite subcover of X. That is, there is a finitely many points x1 is to x, and so the X equal union of B epsilon xi. So, however, the converse not true. So, so of course, this is not the case with every totally bounded metric space. So now, okay. So now look, the converse not true. So, for example, consider X equal open zero visual metric, then X is totally bounded. Now, this is because if we take any epsilon greater than 0, we can choose a natural number n such that 1 by m is an epsilon. So there is a finite many points 1 by n, 2 by n, daughter n minus 1 by n belongs to X as X equal union of B epsilon I by n. Okay. However, X is not compact. Okay. So then the open cover 1 by n cover 1 does not admit a finite subcover. So that is the argument. Okay. So I hope this is clear. So let me know if you have any doubt or any question from till now. I shall wait for a minute. Okay. Hmm. So now let's start with the next question. Question that show that every subset of real line with cofinite topology is compact.
Excuse me. Hello, sir.
Yeah,
Please
Mustaq.
repeat the first one, please.
Okay, Mustaq. Sure, Mustaq. Okay. So as per he requested, so let's get to the first question itself. So the first question is that um, so suppose it's a compact topological space, and if it's a function of x is infinity to be continuous as that, I mean we need to show that we have some r greater than 0, so the fx has that r as a lower bound. Okay. Kindly wait a minute. Let me check the argument itself by myself. Kindly wait a minute. Okay. So, so now, look, if it is compact, okay, and suppose the x is given to connector, if it's compact connecting a subset of a real line, this means what? If x will be of the form closed interval AB, and if x is not compact, so fx can then fx that fx will be of the form a1 b1 and inverter a and bn. So if you take the minimum of that, the fx value is greater than equal to a. Okay? So that is the argument. So basically here you need to use the fact that in real and compact considerment closed interval AB. This is the compact plus connected set in R. Okay. So this is the main trick here. Okay. Do you understand, Mr.? Do you understand, Mustaq? Okay, I have it clear to everybody. Okay, so now let's get back to the original question. Kindly wait a minute. Okay, now, okay. So what is the question? The question is that so that every subset of R cofinite topology is compact. so that every substitutable cofinite topology is compact. Okay, so how to do? And so I don't know, but this question has already been solved in the previous session. But anyway, let's again look into the argument. Okay, so we have added the cofinite origination is compact. So what we need to do? So we need to start open cover. So let U alpha be an open cover of R. Okay. Now in so this implies what? Each R minus U alpha is finite. Okay. So choose some index element from the index set. Now since that R minus U alpha naught. Okay, now since R minus U alpha naught is finite, so suppose this finite set is only x1, x2, xn. Okay, now let xi belongs to U alpha I for some alpha I. So these implies what? These R is equal to U alpha 1 dot dot U alpha n dot dot U alpha 0. This is what? This is a finite subcover of Q. So these implies what? These implies R with cofinite topology is compact. So let me know, do you understand the argument or not? So basically what we have done, we start with some open cover U alpha 1 minute. So we start with open cover U alpha. Now since R minus U alpha finite, we can take an alpha naught. Now since R minus U alpha naught is finite, suppose this set is x1, x2 dot xn. Okay, and so since the and let the x1 and suppose this xi belongs to U alpha. So these implies this whole set R is equal to u alpha 1 dot dot union v alpha 1, which is a finite subset of u. So this tells what? This tells R cofinite topology is compact. Okay. So these are going. Okay, so one thing you need to observe is that this argument will work for any infinite set with cofinite topology. This argument will work with any infinite set with cofinite topology. Okay, so this, so okay, so now let's okay. The next question: show that every uncountable set with co-countable topology is linear. Every uncountable set co-countable topology is linear. How to do? So, okay. So, one minute. Kindly hold a minute. Let me add the camera here. Kindly hold a minute. Kindly wait a minute. Okay, so our going on, it seems there is some issue with the camera itself. Anyway, so let's start solving. Okay, so okay, so kindly wait a minute. It seems that there is some issue with the software itself in the Windows. Kindly hold a minute. Okay, so so one minute. Is everything fine or not? Okay, hmm. So in this question, what we need to show? We need to show that every uncountable set with co-coordinate topology is like that. Okay. Okay, so here we are going to show that every uncountable set to countable topology will envelope. Okay. So uh, so what we can do is it envelope or it will also be all envelope. Okay. So basically we can show actually compact. Okay. So how to prove it? So let x.
Hello. Sir,
Yes,
please
please.
repeat the third question.
Uh, Third question. Okay. Okay. So, uh, okay, so it's in the Mustafa's left. Okay, anyway, since he has left, so anyway, I will upload the recording so you can go through that. So let with the third question itself. So before so first this okay. So let's go to third question. So the what is the third question? Third question is that if we have the metric space and x in the sequence converges to some point, we need to show that x in Unix is compact. Okay, finally. Okay. So okay. So since U alpha is an open cover of Xn such that X belongs to U alpha. Okay. So U alpha is open cover of Xn union X. Now since Xn goes to X, so there exists an n rectangular case of Xn goes to U alpha, not for all n rectangular. Okay. And suppose Xi belongs to Ey. This implies what? This implies E1 dot alpha. This is equal to Xn union X. And this tells that Xn union secret and X is compact. Okay. So this is the argument. So the argument goes as follows. Choose an x belongs to U alpha. Then that x belongs to U alpha not for alpha alpha not. Now since U alpha not, since the sequence xn converges to x, so and since x belongs to U alpha not, so except the finite number of terms of the sequence, all the terms after certain step will lie on the U alpha. Since only the finite number of terms left, so those finite points will lie in the finite portion of U alpha. This is what U1, U2, U alpha not. It's a compact subset. Okay. So these are arguments. Do you understand, sir?
Yes, yes, yes.
Okay, Mr. Hmm. So, okay. So now let's go to the our actual problem. So the question was that suppose x if x is a co-countable topology, uncountable topology, then x is length. How to prove that? So let x be uncountable set with co-countable topology. Okay. Now, okay. So since x is uncountable, so to choose a countable subset of x. Let it be of the form x1, x2, xn dot dot dot. Okay. Now define u1 is equal to x minus x2, x3, xn dot dot. u2 is equal to x minus x3, x4, x5 dot dot dot. un is equal to x minus xn plus 1 comma xn plus 2 dot dot dot. Clearly this ui is open cover of x. So this ui is open cover of x, but of course it does not have countable, so it does not have finite subcover. Why? Suppose let x equal to u I1 dot 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 u I n. Okay. Now take n greater than this I1, I2, I n. Okay. Then clearly this xm does not belongs to the union of ui1, union of uin. Okay. So this implies what? That union does not cannot be full of x. Correct. So this tells that x cannot be compact. Okay. So let me repeat the argument. Well, so note that actually this question has been given in the uh, as for only real line. Okay. But the same argument can, I mean, the same argument can be put in the real line. That's why I give a generalized solution. Co-countable, uncountable set, co-countable topology in the lab. X uncountable set, co-countable space. Okay. Choose uncountable subset of x. Let it be x1, x2, xn. Define u1 is equal to x minus x2, xn, u2 is equal to this. Clearly, this u is an open covered access. It does not admit a finite, so we need to show. So let x equal to ui1, u2, ui. Take m greater than I1, I2, I. Okay. The xm does not ui1 or ui. Okay, so that is our goal. Okay. Okay. Now let's go to the next question. So oh, 1 minute. So So amino acid asked me to repeat this question. Okay, so let me repeat it. So it's an uncountable set. So okay, so since it's an uncountable set, so we can choose a countable subset of x. Okay, so suppose this is x1, x2, xn. Okay, now define u1 is equal to x minus x to xn and u2 is equal to this, u1 is equal to. Now clearly u1 is an open cover. Okay, so it does not admit a finite subcover. Let x equal to uy1 uy and take m greater than, I'm sorry, so suppose m greater than I1 or im. Then of course, then that xm does not belong to u. So that's so that this tells that that union is not a countable subword. Okay, so it's not a finite subword. So Avinash, let me know, is this clear to you? Okay. So I hope this argument is clear. Okay, so now go to the next question. Let S be a set. Collection script A of subsets of X is said to have one. Huh. S be a set. Then a collection descriptive of subset of X is said to have a finite intersection property if for every family A1 into An of elements of A have intersection A I is equal to 1 and known it. Okay, so the argument. So I shall back for after 2 minutes. So, how to solve this? Okay. So if the subset, so his find is a property. Okay. So let me. Now the question is that prove that a topological X is space X is compact if and only if for every family of closed sets having finite intersection property has non-intersection. So topological. So this is what you need to prove. So how to prove that? So look. Hmm. So okay. So let X be compact. Okay. So let X be compact. Okay. And let the I be a family of closed sets. Okay. Let X be a compact. So so it's a family of closed sets. Okay. Now we need to show and suppose let this family A has finite intersection property. Suppose this family of finite intersection property. Okay. What we need to show? We need to
Repeat the last question.
AI. Oh, okay, Mr. Okay, so let's finish this question. Then let's repeat the last question. Okay. So since let's finish this question, then only I will repeat again the last question. Okay. So we need to show the intersection AI is non-empty. Suppose intersection AI is empty. Suppose the intersection AI is empty. Okay. So these implies what? These implies union of AI complement is full of X. These implies what? This state X minus AI, this state, this collection forms an open cover of X. Okay. So this implies this collection has finite subcover for X. Okay. So let X equal to union of X minus AI, I is equal to J1 to J2. So this implies what? This implies intersection to I is equal to J1 to GK is empty. But it is a contradiction. Why? Why? Because our chosen capital A satisfies A5. Okay. So that is every finite collection has a non-intersection. Okay. Okay. So yeah. So this is one side. So X is compact. So A being family of closed subset, then A has a finite property. We need to show intersection AI is not. Okay. Suppose intersection AI is empty. This implies what? Union of AI complement is full of X. This implies X minus AI. This forms an open cover of X with a finite subcover X. Now let X equal to union of X minus AI. That is intersection I is equal to J1 to J. So here's a contradiction. Okay. So this is the argument. Okay. Think about, let me know the way out, or else we can go for the converse. Okay, now okay. So now for the converse part, what one can do? Conversely, let's suppose this holds. Okay. Now, so suppose every like family of closed set having if it has non-intersection. Suppose this hold. Now we need to show X compact. Okay. So start with an open cover. Okay. So we need to choose finite subcover, right? Okay. So it's an open cover. So okay. So X equal to union of U alpha. Okay. This is what empty set is equal to intersection of U alpha complement. Correct. And this U alpha complement is the family of closed set of X. Okay. Seen so these implies what? These imply U alpha complement does not have finite intersection property. So this implies what? There exists a finite subcollection complement which does not have, I mean, so there is finite U alpha which have empty intersection. Okay. With empty intersection. So this implies what? Well, so 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 this implies there exists alpha I1 dot alpha I k such that intersection U alpha I L equal to 1 to K MT is equal to empty. So this implies what? X equal to, you know, U alpha I L is equal to 1 to K. Correct. So these implies what? These implies X is compact. Correct. So this is the argument. Think about it and let me know. Do you have any doubt or any question or confusion? Okay. 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 So I hope this question is clear to everybody. Now, as Muskan asked, so let's get back to the previous question. Okay. So before going to previous question, 1 minute. Okay, so this question is basically, I mean, so you can treat this question, this in question you will find the property you can treat as a question where a state having, I mean, so you can think it's this is a criteria of a subspace of a space being a compact space. Okay, let S be a state. So okay, so no, okay, so let's go to the previous question. So in the previous question, what else? Our we need to show that every co-countable, co-uncountable with co-countable topology is length. Okay. Okay. So, uh, here it's uncountable. So, okay, so we can find a countable subspace of X. Okay. So call the counters of x1, x2, xn dot dot dot. Okay. Define u1 to be x minus x2, x dot dot, u2 to be x minus x3, x3, x4, x3. Okay. Then clearly ui is an open cover of X, and it does not have a finite subcover because since x equal to ui1 or uin and m greater than I1 or in, then xm does not have ui1 union ui. Okay. So that's the argument. Okay. Okay, so there is the argument. So now let's go to the next question. Next question is the following. Let each D be a matrix. Let A and B be disjoint, non-empty, closed subsets of X such that B is compact. Then show that zero exists R greater than 0 such that for all X belongs to A and all Y belongs to B. We have Bxy greater than R. And second part, give an example of a metric space X and true two non-empty disjoint closed subsets A and B that given R greater than 0, there exists X belongs to A and Y belongs to B such that dxy less than R. Okay, so the question, yeah, the question is right. I was checking the question is correct or not. So if a metric is space and A able to disjoint closed subspace, okay, B is compact. Show that there is R greater than 0, so that for all X belongs to and all Y belongs to B, dxy greater than R. And we need to give an example of a metric of X with two non-disjoint closed sets, so that this does not follow. Okay? Think about it. I shall be back after 2 minutes. Well, so okay, again camera unavailable, so there is some issue with the camera itself. Sorry, not camera, the software itself. Okay, anyway, so how to solve this question? Okay, so this problem can be done as follows. Okay, this is quite tricky problem, so let me write an argument here. Okay, okay. So since A complement is an open subset of X containing B, we see that for every X belongs to B, there exists Rx greater than 0 such that B 2 Rx of X subset of X minus A. Now, since B is compact, the open cover B Rx by 2 of X of B admits finite subset. Okay, say B Rx1 by 2 of X1, B Rxn by 2 of Xn. Now choosing R is equal to half of minimum of Rx I is equal to 1 to N, we see that given any X belongs to B and Y belongs to A, dx y is greater than R. Okay, so dx was greater than R. Okay. Or alternatively, so this is one way, and alternatively, define function if x belongs to open 0 infinity by f of y is equal to d of a of y. Okay. By definition, in form of dy x, x belongs to its control. Since B is compact by Weierstrass theorem, it attains its minimum R. Say, say Z belongs to B. Such that 0 less than R equal to if Z less than equal to f of y. For all y equal to B. For all y belongs to B. Okay. So, then by definition of f of y, we have f of y less than equal to dxy for all x belongs to f. And for the second part, consider x equal to r square with Euclidean metric and a closed x comma 0 with x belongs to, and b is equal to x comma 1 by x with x greater than 0. Then given any r greater than 0, choosing n belongs to n with r greater than 1 by n, we see that there exists n comma 0 belongs to f and n comma 1 by n belongs to b, such that d of n comma 0 and n comma 1 by n, this is equal to 1 by n less than r. Okay, so this argument. So this argument. So basically in this question, what were 1 minute. So basically in this question, what we need to do. So if this can be solved in two ways. In usual way, suppose A complement, then obviously A complement is open set containing B. So for every x belongs to B, we have some Rx greater than 0, B2 Rx. Now since B is compact, so the open cover Brx by 2 of Br with a finite subword, say Br. Now choosing R equal to half of minimum Rx, so we see that given in x belongs to B and y belongs to A, dxy uh, greater than R. So now, so we can now define f equal to from x to 0 infinity by f of y dy continuous. Okay, 1 minute. Let me check everything was fine or not. So now since B is compact, now by Weierstrass theorem it attains a minimum, say Z belongs to B. So the 0 less than R equal to Fz equal to f of y. By definition of f of y, we have that f of y or d of xy for second one. Now consider x equal to R2 is clear metric and a closed subset, and A is equal to x comma 0, B is equal to x comma 1 by x. Then given in R greater than 0, choosing n belongs to R greater than 1, we see that there exists a point n greater than 0, n comma 0 belongs to A, such that that relation holds. Okay, so this is the full argument. Okay. Okay, so now let's ask some interesting question. Okay, so now below I am drawing two figures. You need to show that are the homonym or not. Are the following figures homeomorphic? These are circle in the figure. Now you need to show that the are these two following figures homeomorphic or not. Think about it. I shall wait for 2 3 minutes. Think about it and try to tell whether. Okay, so let's uh, Okay, so look, the point is that if you remove this point, then it will become what? Disconnected, right? But if you remove one point here, then it still remains connected. So if these two spaces are homeomorphic, then removing one point also they will be homeomorphic. But after removing one point, one remains connected, but other becomes disconnected. That's why these two spaces cannot be homeomorphic. Okay. So this is the argument. Okay. So that's all for today. If you have any doubt, you can ask me today, or you can ask in the next live session. Okay. You can drop an email. I shall get back to you as soon as possible. Okay. So let's stop here. We shall meet on the next Saturday. Sorry, next Friday, and then the upcoming Saturday, and that will be the last class. Okay. So if any doubt, please ask in that in those. Please try to use those sessions. Okay. So okay. So let's end the meeting here.